So, last class I have discussed how we can determine the thickness of the seal for open well, or the thickness of the concrete seal for the open well, and I was discussing one particular example problem. So, in example problem that it is a circular cross section, and then the grip length is 8 meter, and the well is passing through a soft clay layer whose Cu value is 25 kilonewton per meter square, and resting on a stiff clay layer whose Cu value is 100 kilonewton per meter square, and inside radius is given 2.25 meter, and we have to determine what would be the required thickness of that seal. Okay. So, now so that outside radius is also known, and that is R0 is equal to 3 meter. So, the total outside diameter is 6 meter and inside diameter is 4.5 meter. So, R0 is 3 meter, Ri is 2.25 meter. So, we have to check determine the thickness. So, it is a circular cross section. So, T will be 1.18 Ri root over Q Fc. Okay. Now, Q is roughly we can calculate by H into gamma W minus T into gamma C. Now, this is unit weight of the soil, that unit weight is given as 18. Okay. So, that unit weight of the soil is given 18 kilonewton per meter cube. Okay. So, unit weight of the soil or saturated unit weight is 18 kilonewton per meter cube. This is gamma sat. So, this is gamma sat, which is 18 kilonewton per meter cube, and obviously, the soil will be saturated because it is below the water level. So, that means we can write that sorry, this is not 18, this is 20 kilonewton per meter cube. So, gamma sat is 20 kilonewton per meter cube, and then yes, gamma sat is given 20 kilonewton per meter cube. Anyhow, that unit weight may not be required, but it is given that gamma sat is 20 kilonewton per meter cube. So, now what is the buoyancy? I have stress or the pressure due to the buoyancy. The H is 18 meter, total height of the water level from the base, because buoyancy is acting at the base. So, that is equal to 3 meter, that is equal to 10 meter and plus 8 meter. So, this is 10 plus 8, that is 18 meter. So, total height H is equal to 18 meter. Okay. So, that means this is 18, unit weight of water is 10 minus T we do not know, and this is 24. So, this will be 180 minus 24 T. This is the 24 is the unit weight of concrete, and then Fc we have taken as 0.1 Fc dash, because the range is 0.1 to 0.2 Fc dash. So, we have taken 0.1 Fc dash. So, that means here this is equal to 0.1, and the 28 days compressive strength of the concrete is also known, and that is 20 MPa. So, 28 days compressive strength of the concrete, that is known. So, that is 20 MPa. So, this side all the known properties are given, and this side we are calculating all the unknowns. That means, this side all the known properties are given, and this side we are calculating the unknowns. So, that means, the Fc dash is given as 20 MPa. 28 days compressive strength of the concrete is 20 MPa. So, this is 0.1 and 20,000 kPa. So, this is equal to 2000 kilonewton per meter square or 2 MPa. Okay, so, now if I put these values, then I will get what is the T 1.18, then Ri is 2.25 root over Q, which is 180 minus 24 T, then Fc is 2000. Okay. And then if I solve this equation, because we have a T in this side and T is within the root also. So, we have to take both sides square. Then if I solve this equation, then T is coming out to be, after solving, is 0.75 meter. So, the thickness of the seal is coming out to be 0.75 meter. Let us see whether that thickness is sufficient or not, and that we have to check by these two checks. So, first check that we will do for the buoyancy, and we know that Fu is pi r outside square into h gamma w, and this is pi outside radius is 3 meter into 18 into 10. So, this is 5087 kilonewton. So, that is the amount of buoyancy force which is acting. Now, we have downward forces, and that is the weight of oil, weight of seal, and the friction force due to the friction, and then the weight of oil is equal to. So, these shafts, that means if this is a circular cross section, cross section. So, this weight of this shaft we will only consider at this stage, because is at this stage there is no other components are present, only the shaft and the seal at the bottom. Okay. So, these two weight we have to consider. So, weight of the oil means weight of this shaft, and weight of this shaft will be pi r 0 square, this is d 0 square, this we have taken pi divided by 4. So, this will be d o square, and this is d I square. Okay. That is the area of this solid portion, and then the weight of the concrete is 24, and then the weight or length of this shaft. So, what is the length of this shaft? This is 8 plus 10 plus 3. Okay. So, that the length of the shaft is 8 plus 10 plus this 3. So, this is 21 meter will be the length of this shaft. So, now if I provide this r 0, d 0 and d I value, this is pi by 4 into 6 square minus 4.5 square into 24 into 21. So, that is equal to 6231 kilonewton. That is the weight of the well. Okay. Now, weight of the seal, that is inside radius pi r I square into T into weight of the concrete. This is pi I is 2.25 square into 24 is the unit weight of the concrete, and thickness is provided is 0.75 meter, that is the thickness. So, this is equal to 286 kilonewton. And now, for this case we are neglecting the friction force. So, if it is safe against this weight of oil and weight of seal, then if I add the friction force, then it will increase the safety. So, So, now we are checking considering friction force contribution is 0. Let us see whether safe or not. So, that means the total downward force F d is will be 6231 plus 286. So, that is 6517 kilonewton, which is greater than 5087 kilonewton. So, it is safe. So, even if we consider without considering the QS, it is safe. Even if we consider the QS, then definitely it will be over safe. So, but right now this is safe against that buoyancy. Let us see whether it is safe against the shear or not. So, the second checks that the shear stress developed is equal to A I H gamma W minus A I T gamma C divided by P I into T. Now, if I put all these values, then A I is 1 by 4 pi, this is inside area for the well, that means this 4.5 whole square. Then H is 18, unit weight of water is 10, again pi by 4, 4.5 square, then thickness is 0.75, unit weight of concrete is 24. Then divided by inside perimeter is, this is a circular section, 2 pi inside radius 2.25, then the thickness is 0.75. Okay. So, this value is or first we calculate in terms of kPa, 243 kilonewton per meter square or 0.243 MPa. So, the shear stress which is developed is 0.243 MPa. Now, the ultimate or the permissible shear stress, which is 0.17 F root FC, 0.17 phi root FC. So, this is 0.17, phi is 0.85 and FC is, this is in MPa, because this is in MPa. So, that means this will be 2 MPa, because the FC value is 2 MPa. So, we are putting 2 and that is coming out to be 0.204 MPa. So, that means you can see that tau is greater than tau u. So, it is not safe, because the amount of shear stress which is developed is greater than the permissible shear stress. Okay, so, now we have to go for the next trial. Now in the next trial we are taking the T is equal to 1 meter. We are increasing that, because other conditions are safe, only you have to save against this shear. Now, the tau which is developed is, if I take this pi by 4, 4.5 outside. So, then this will be 18 into 100 minus, now it is 1 into 24, then divided by again 2 into pi into 2.25 into 1, because now it is 1 meter. So, that means it is coming out to be 176 kilonewton per meter square or 0.176 MPa. So, now tau is less than tau u. Okay, tau is, we will not change. So, tau is 0.24204 MPa, it is 0.176 MPa. So, there will be I mean it is safe against shear also. Now, the question is that why we are calculating the shear between this well and the shaft, because when we apply the concrete for the bottom seal, then initially, so that strength, this strength of the soil, the strength which is gained in the 28 days that we have considered. So, there will be a shear between this seal concrete and the shaft. Okay. So, that is why that shear stress we are checking here, and there will be a buoyancy also that we have already checked. So, these two checks we have to done, and then based on that we have to provide what would be the thickness of that bottom seal. So, here initially by calculation it was coming 0.75 meter, but when we did the checking for buoyancy it was fine, but for the shear checking it was not safe. So, we have to increase it, and we have provided now 1 meter. Now, all the conditions are satisfied. So, we will provide the 1 meter thickness or 1 meter thick concrete seal or bottom seal for this particular case. Okay. So, next one that I will discuss, the estimation of bearing capacity. So, this we have the checking for the that concrete seal for the open well. Next one, how we can determine the bearing capacity for well foundation. So, for estimation of bearing capacity, so which is also same to the pile foundation, that means the ultimate bearing capacity or load carrying capacity of the well is QP, that means tip, plus QF, the friction contribution. So, this is the tip contribution, this is the friction contribution. So, summation of these two under compressive load. So, now Q tip will be equal to the area, base area, this is the base area of well into the bearing capacity factor NC star, then plus Q dash NQ star. Okay. So, we have neglected the third component, because we did it for the pile foundation also, which is small compared to the second component. So, we have considered first for the cohesion part and then the second component. If the C is 0, then there will be only the second component. So, now this is QP ultimate, okay, or QP ultimate. Now, if I want to determine the QP net or net ultimate, then that will be again AB C N C dash plus Q dash effective overburden pressure in Q dash minus Q dash, that is that will give us the net. So, this will be AB C N C dash plus Q dash N Q dash minus 1. Okay. Now, for sand or granular soil, where C is equal to 0, then the QP net will be equal to simply AB Q dash in Q dash minus 1, where in Q dash is effective vertical stress or overburden pressure at the base of well. So, this is for the Q tip part. Similarly, for Q F friction part, so that will be the same as the pile foundation. So, that is 0 to D, that means the total depth of the well, then this is the friction resistance, perimeter, friction resistance and dz. Okay. So, that will be same as pi d outside, that is the perimeter, then the k, okay, and then the tan delta, and then the vertical stress that we have to integrate sigma v dash dz, the same way that we did it for the pile foundation. Okay. So, now we can put the value and finally, we will get. So, this is equal to half, then pi d 0, which is the perimeter, into L square, or I should write d square, which is the depth of the well below the scour level, d square into k into tan delta, okay, into gamma. So, that means here the same way we are doing it. So, that means that this is changing. So, that means here it is, you can say the gamma dash into the d, if this is the depth of the well below the scour. So, that means this is, if this is the scour level and this is the well foundation base. So, this is the depth or the grip length. So, this is equal to d. So, along that there will be a friction between the soil and the well. So, this is the scour level. And below that this is d. So, this is gamma d. So, that then the horizontal force that will act sigma h, that will be gamma d into tan delta, into k. So, that is the horizontal stress, gamma d into k, and then that we have to multiply with the tan d, that will give you the frictional resistance along the shaft. So, that is we are doing here, and then if I take the total force, and that we have to take the average. So, that will be half into, so total force will be half into gamma d into again the d into k, okay, and that will be again into tan delta. So, this is half and this is perimeter gamma d square k tan delta, and that is acting along the perimeter. So, this is basically the FC, okay, and then if I multiply with the perimeter, then I will get the total friction resistance, which is same as the pile calculation, pile friction resistance calculation. And remember that this again I am telling that this equation directly we can use if it unit weight is uniform or same, but there is any water, suppose there is any water, okay, then this will be the distribution. But in this case, this is the common distribution because it will be always below water. So, this type of distribution will not occur. So, because the grip length portion of the well will be always below the water. Okay, so, that means here we can directly use this equation by considering a triangular distribution, and this is the effective unit weight we have to consider. That means, if it is below the water, then you have to consider the submerged unit weight, which is gamma sub or gamma dash. So, this way we can calculate the friction resistance and the tip resistance for the pile for the well, and the NQ dash value I can get from this chart. So, this is for different friction angle for sand, and then from here I can get what is the NQ dash value, and that NQ dash value we can put here. So, that means the finally we will get another thing is the how we can calculate the K, because delta is the friction angle between soil and the pile or the well, and the K is taken as 1 minus sin phi. Okay. And then delta we can take as 2/3 of phi for this particular case if no information is given. Otherwise, I have discussed that what will be the delta for concrete under different condition for during the pile foundation, that delta also you can consider. Okay, so that means here we know that K will be 1 minus sin phi, delta I have discussed. So, this way D we can determine the friction resistance and the tip resistance. So, D0 is equal to here is the outside diameter of well. Okay. So, next one that I will discuss that how we can calculate the bearing capacity for if the well is in clay. Okay. So, if it is in clay, okay, before I go to the clay, so here we can calculate the ultimate bearing capacity, that means the Q ultimate, which is equal to Q P net plus Q F. So, I will get the ultimate bearing capacity. Okay. And then if I apply the factor of safety of 2.5 to 3, then I will get the safe bearing capacity, that you know. But IS code has recommended bearing capacity or bearing pressure which is allowable bearing pressure. So, allowable, you know that here the settlement consideration is also incorporated. So, that means here the bearing and the settlement consideration are incorporated, and minimum of these two will give you the allowable bearing pressure. So, that means here settlement is also incorporated. So, this IS code has given the allowable bearing pressure in terms of N value. So, this is the equation where this is in kg per meter square. Remember that N is the corrected SPT value at the base of the at the base of the well, and B is the smaller dimension of well section. For smaller dimension of the well section means, suppose if it is a rectangular well, so this is B or this is L. So, among this B is the smaller. So, that is why B will be here the dimension of the well. So, that can be in any direction, and D is the depth of foundation below the scour level, and that is in meter. So, remember that this is kg per meter square, this B is in meter and D is also in meter, and if it is a circular well, so B will be, you can consider, is equal to D, diameter of the well. So, using this equation we can directly get the allowable bearing pressure. Now, for the clay ultimate bearing capacity we can determine as, and remember that this is applicable for again for sand, cohesionless soil. This equation is applicable for cohesionless soil. So, for the clay where phi is equal to 0, then Q P net is equal to A B, then C U N C dash, okay, and Q F is equal to again the summation of alpha dash C U then P D L, that we are doing for the pile. Okay, so, here we have taken the summation, because if for different layer we have to determine the QF and then you have to add. So, then here the NC dash is taken as 9 like the pile foundation, and AB you know that will be pi d0 square by 4, okay, and alpha dash is suggested as 0.21 plus 0.25 then PA divided by Cu, and that should be less than 1. So, where PA is equal to atmospheric pressure, which is actually basically 100 kilonewton per meter square, and Cu is the Andren coefficient, which is also in kilonewton per meter square. So, if I know the Andren coefficient of the soil, and then we can put this value here, Pa is always 100 kilonewton per meter square, then we will get the alpha dash value, and that should be less than 1. So, this way we can calculate the alpha dash for different layer, and once we get the alpha dash, we know that we have to multiply it with Cu, then we have to multiply the perimeter and the length of that segment of the pile or the well, and then similarly in the tip also we can calculate in this way. So, finally, Q u will be Q p net then plus Q f, okay, and Q safe will be Q u by factor of safety, which you can take as 2.523. Okay. So, this way we can determine the unit bearing capacity of the well in sand as well as in clay, and IS code also given direct equation based on the SPT value, by which also we can determine what would be the allowable bearing capacity of the well. So, in the next class I will start that another section of well foundation, which is the lateral stability of the well if the well is subjected to lateral load also, because these well are generally capable to a large number of lateral force. So, we have to check the lateral stability under that lateral force also. So, that I will start from the next class. Thank you.